Evening, everyone. Welcome to the Edinburgh International Conference Centre. For those who have been here before, welcome back. For those who have joined us for the first time, it's very nice to have you here, and thank you for spending your time with us. I know we're competing with the football, but hopefully this will be a bit more entertaining. My name is Rob Turnbull, and I am the Sustainability Manager here at the EICC. I help to organise these events as it sits within our wider sustainability programme. It's an initiative designed to foster community engagement with the events that we host within these walls. It's designed to bring people together, share knowledge, spark conversations, and inspire positive change. This sits right at the heart of what EICC does. Our motto is to create an environment which inspires ideas that change the world. Over the years, we've welcomed speakers on everything from climate action to well-being and social inclusion. Many of our previous talks are actually available on YouTube. If you simply search EICC venue, you can see all the previous talks on there, and you can watch them at your leisure. At the EICC, we host conferences across a wide range of disciplines, topics, sectors, and this week is no different. This week we are hosting the European Physical Society Conference on Plasma Physics, and that's a mouthful. So we're especially pleased to be collaborating with them this evening. We're especially pleased to welcome Professor Neil Turok here. He is the inaugural Higgs Chair of the Theoretical Physics at the University of Edinburgh. He's one of the world's leading cosmologists, and we're delighted he could spend the evening with us. He's going to have a wee talk with us, explain the simplicity of the cosmology, the cosmos, hopefully in a way that I might actually be able to understand it. After the talk, he'll be joined on stage by Professor Fulvio Militello, and I hope I got that right. Yay! They'll have a bit of a discussion about their works and their careers, and then we'll open the floor to a Q&A session. So please think about questions you have to ask, and you can ask them then. However, just before I begin, a little bit of housekeeping. So there are no planned fire alarms this evening, so if the alarm does go, please use the exits as directed and exit the building promptly. And also please note that tonight's event is being filmed. Now, without further ado, please join me in welcoming Professor Fulvio Militello to the stage.
Thank you for the introduction. My name is Fulvio Militello. I'm a fusion scientist, so quite different from cosmologist. And I'm also an executive director of UKEA, United Kingdom Atomic Energy Authority. And tonight I will try to facilitate a little bit of discussion, and this is going to be a great evening of science. Now, Neil has achieved so much in life that I could not remember it all, so I had to write it down. So I will just read it from my notes. Neil Turok is one of the world's leading theoretical physicists and cosmologists. He's the Higgs Chair of Theoretical Physics here at Edinburgh University, and formerly served as director of Perimeter Institute for Theoretical Physics, one of the world's foremost centers for fundamental research. His work explores some of the biggest questions in science. How did the universe begin? Why does it look the way it does? And what are the fundamental laws that govern reality? Over a distinguished career spanning Princeton, Cambridge, Edinburgh, and Perimeter, he has made major contributions to our understanding of early universe, and he has collaborated with some of the most influential physicists of our time, Stephen Hawking, Roger Penrose, and more. He is also a passionate advocate for science education and opportunity, having founded the African Institute for Mathematical Science, AIMS, a network that has helped train thousands of young scientists in Africa. Neil is the author of the acclaimed popular science book, The Universe Within, which became a bestseller and won Canada's Lane Anderson Award for Science Writing. His scientific achievements and international leadership have been recognized with numerous honors, including the James Clerk Maxwell Medal and the John Torrance Tate Medal for International Leadership in Physics, and appointed as an officer of the Order of Canada. Renowned for both the depth of his ideas and his ability to communicate them, Neil has become one of the most influential public voices in modern physics. So tonight's lecture asks a wonderfully intriguing question. Is the universe simpler than what we imagined? And now, as a fusion scientist, when in fusion, nature seems to be determined to express itself in the most complicated way, I'm actually quite interested in this claim. So, Neil, the stage is yours. Thank you.
Thank you very much. Okay, thank you everybody for coming to hear the story of the universe. And thank you very much to Fulvio for inviting me to give this lecture as a side event to the European Physical Society meeting on plasma physics, which is taking place in Edinburgh this week. So I'm going to tell you a story. That's what theoretical physics is. It's a story about reality. And this story is based on the key idea is that the discoveries we've made in physics recently, the observations and experiments, point to an unexpected simplicity. Okay, so people like me, theorists, and I refer to us as imaginary people. We imagine things. We never actually discover the truth. We just imagine lots of possibilities. And then there are real people who are experimental physicists who do the experiments and gather data, and astronomers who make real pictures of real things. They're the ones who actually discover the truth. We just encourage them to look in certain ways. And so what's happened is people like me and my generation of theoretical physicists ended up with a very, very complicated picture of the universe and how it works. So you may have heard of string theory and extra dimensions and supersymmetry and the multiverse, the most, elaborate theory anybody has ever made up. There's not just a single universe and many universes. They're all different, and so on. So this field, my field, has got into this incredibly complex and confused state. Okay, so what I'm going to tell you about today is a very radical point of view, my point of view, that no, what the data are telling us is that actually the universe is remarkably simple. It's not simple on our scale, as I'll explain. On our scale, the scale of our everyday lives of human beings, it's really complicated and we can't predict anything. Okay, but on the very large scales, the largest scales we can see in the universe, it's unbelievably simple. And on the tiniest scales, the scales we need very powerful microscopes to see, again, it's very simple. Okay, all the complexities in the middle. So that'll be the theme of the talk. And what I like to say is that we, theoretical physics, study the world at its simplest level, okay, where it's easiest to understand. I know the mathematics looks complicated, but what I mean by simple is predictable, is that we can, through a lot of hard work, we can understand what's going on and then predict it with extreme precision. Okay? Now that's the easy part of science. The difficult part is the stuff in the middle, right? It's life, it's psychology, it's consciousness, it's what society does. And that part, physics really has nothing to say yet about. So I'm going to tell you about simpler cosmology than you will read about in the popular media. And so this, as I said, amazingly, this is a radical idea that after all the universe is not this complicated mess, which is the most popular paradigm. And I have to mention my collaborator who's at Edinburgh, Latham Boyle, and also some very bright, talented students drawn to Edinburgh to work with us who are really driving these ideas forward. So let's begin with ancient history. So imagine you are cave people and you're looking at a fire, and I guess people were doing this in Scotland long, long ago. And you're wondering how the fire works. Oh, I think they want you to move over there. Your friend is over there. Okay. So, staring at a fire, what do you immediately see? Well, it has two properties. It has a color, right? Certain color, and if it's red, it's cooler, and if it's white, it's hotter, or very light, bright yellow, it's hotter. So people knew that. So there's a correlation between the color and the temperature. Okay, that's an essential feature of a fire. And where does that correlation come from? Well, it comes from quantum mechanics. Okay. Max Planck, who was the founder of quantum mechanics, was assigned the problem of figuring out the color of electric light bulbs and how to make them as bright as possible. So he was essentially doing this, thinking about what determines that color, and it's quantization of the particles of light. So if you really got to the bottom of how a fire works, you would find that it actually would not work unless the light came in packets of energy, and the lighter the color, so if you go from red towards yellow, the more energetic the particles of light. Okay, and if light wasn't made out of particles, fires wouldn't work. Okay, the nature just wouldn't behave properly. In fact, the whole thing would just disappear. It wouldn't even be consistent. So now, understanding natural phenomena quantitatively, sometimes we call this mathematical science, but actually the root of science is mathematics. When we've understood something mathematically, then we really have understood it. Why? Because mathematics is the most powerful logic we know, and if we can match it with natural phenomena, then it becomes incredibly powerful in terms of predicting those phenomena. And where did mathematics come from? Well, it came from Africa. So here's the first known artifact with geometrical shapes on it from 80,000 years ago from South Africa. This is the oldest known, or one of the oldest known artifacts with numbers. It's called the Ishango bone. It's from Congo. DRC, who's playing football this evening. And if you don't want to root for England, then I encourage you to root for DRC. That's what I'll be doing. So this bone is really quite remarkable. It includes groups of notches which are all the prime numbers less than 20. And so somebody was clearly counting in groups of numbers. People speculate about exactly what they were doing. In fact, I've got a replica of it here, which I'll pass around. And you'll see it's rather a beautiful little bone. It's a baboon bone, and it has in its end, in this end, you'll see on the end, there's a quartz crystal embedded in one of the ends, and it was obviously a little writing or scratching instrument. So think of it as the world's first or oldest known office tool. I've seen the real thing. It's in the Belgium Natural History Museum, okay, which is really not the place it should be. It should be in Africa. It's an absolute scandal that it's only possible to see it by going to Belgium. And then here is the world's oldest known astronomical observatory in Nabta Playa in southern Egypt. So, and this dates, this is 7,000 years ago. Okay, so the origin of mathematical thinking and thinking about the universe, certainly like humankind, originated in Africa. And as I say, you probably know about this character, the most amazing supporter of football, who seems to have been excluded from the US, so you're actually not allowed to attend the match. But so this evening, if you watch the match, you will see lots of people imitating him, remembering him. Okay, so that's fire and mathematics. Max Planck, who put the two together, came up with this green curve, okay, called the Planck spectrum. So the green curve was the basic theoretical prediction of quantum mechanics. And it has one parameter, which is this number h, called Planck's constant. And this curve was predicted long before people had the ability to measure it accurately. And then what happened in 1992 is this satellite flew and stared out into empty space, just pure black space and measured the radiation that is coming towards us. This is the radiation from the Big Bang. And the red crosses are its measurements, which lie perfectly on the curve. In fact, these are not the error bars. These are inflated. The error bars are way too small to see. The error bars are smaller than the width of the green line. Okay, so the sky is shining at us with the basic law of quantum mechanics. Okay, so if Planck hadn't figured it out long before, this would have just been obvious. We just need to measure the sky. The universe is telling us about quantum mechanics. So it's a very beautiful thing. Here's the picture of the whole universe that we can see today. Here we are in the middle, the solar system, the sun, and the planets. And then as we look outwards in space, we are seeing the universe as it was further and further in the past, just because light travels at a finite speed. So as we look outwards, we see clouds of gas and galaxies as they form. Go back before the galaxies, we see this web-like structure. This is called the cosmic web. This is the very earliest structures that formed in the universe. And as we go out further, we see this red sphere. So this is a sphere which surrounds us. It's not just you're just seeing a slice through it on the screen. So we are surrounded by a hot surface which emits the radiation that you see in this spectrum. So here's this radiation was released about 380,000 years after the Big Bang, and we can now measure it to very high precision. Let me stand over here. So the remarkable thing, I should say what the blue circle is. If we look back a little bit earlier than that red sphere which surrounds us, so a little bit further out in space, that blue circle is the Big Bang singularity. Okay, it looks like a circle or a sphere which surrounds us, but actually it's a point. Why? Because as you go outwards in space, the universe is getting smaller and shrinking, so it's hard to represent in a picture like this. The blue circle is the last visible, the earliest visible thing we can see, and because it shrinks as it goes back in time, that blue circle is actually a point, and you'll see this in another picture. The surprising thing about these measurements, which have become more and more accurate, so there's now a huge number of these measurements, they're all completely compatible with the known laws of physics and 5 additional ingredients. One of them is called the cosmological constant. This is actually the very first idea Einstein had in trying to describe a cosmology, namely a universe that is actually a solution of his equations. So it's a very simple form of matter. It's absolutely uniform in space. It doesn't change in time. And this form of matter comprises 70% of the energy of the universe. Okay, so Einstein anticipated this by 100 years before it was measured, almost 100 years before it was measured. He just said, what would be the simplest possible stuff in the universe? And it's just some form of energy and matter which is absolutely uniform in space and doesn't change in time. And it eventually turned out that is 70% of what's there in the universe. Then we have dark matter, and you've probably heard about this. Sometimes people call it the terrible cosmological fudge factor, that we have to introduce an additional kind of matter on top of the stuff we're made of. I'm going to tell you what it is. Okay, there's only a theory, but we have a pretty good guess now as to what it is. That makes up another 25% of the energy budget of the universe. And the stuff we are made of is neutrons and protons, nuclear matter with electrons around them, i.e. atoms. And that makes up about 5% of the energy budget in the universe. So that's the energy content of the universe, these 3 things. The radiation just comes for free. And then we have these primordial density variations. So as the universe came out of the Big Bang, it wasn't absolutely uniform. The density varied a little bit from place to place, only by about 1 part in 10,000. So it's a very modest variation. You can think of it like ripples on the sea surface, so tiny variations in density. And these variations caused gravity, the self-gravity of the energy and matter, to be stronger in some places than other. And so where it was slightly denser, the universe collapsed and made galaxies, and in the galaxies they made stars, and so on. And where it was less dense, it expanded and just emptied out into a void. So that's how this web was formed. So the density variations are characterized by an amplitude, it's just the kind of strength of the ripples, and a dependence on scale. And it turns out they're almost perfectly scale-free. So that means that if the density varied by 1 part in 10,000 on a centimeter scale, it would vary by the same amount, 1 part in 10,000, on a scale of, you know, hundreds of light years or millions of light years. So it's the simplest possible type of noise. It's called Gaussian random noise, the statistical pattern we see when we look at this red circle. You'll see it in a moment. And there's a tiny tilt which says that the strength of these variations is gets slightly stronger on large scales, but that's a very small effect. It's only about a 2% effect. Here's a real survey. This is a survey of galaxies that has just been completed, and there are 50 million galaxies in this picture. Each galaxy has about 100 billion stars in it. So the huge number of stars in this picture, and you can see this cosmic web as is shown in this distribution of galaxies. How do you see the dark matter? Strange thing. Some of the matter is dark. It doesn't shine. It's not stars. You see it just like you see water in this bottle, right? We can see the water, although it's transparent. How can we see it? Because it bends the light. Okay, if there's no water, the light travels through in a different way to if there's water. So in the same way as light travels through the universe, if there's additional matter there, it causes a gravitational field which bends the light. And so we see the dark matter by its effect on bending the light behind it. This is a particularly beautiful example where, so here's a galaxy, and then behind that galaxy is another galaxy, which is blue, and would just be a small blob in the picture, except the light from the galaxy behind has come to us in on paths which encircle the lensing galaxy. And this is called the Einstein ring, which was predicted by Einstein long ago, and not even imagined that it would ever be observed. But now we see it all the time. Right, so this is the pattern of intensity across the sky, which is seen by telescopes measuring that red ring. This is the European Space Agency Planck satellite, which made this picture. And so here you see the earliest known thing in the universe, right? This is the fossil radiation showing us how the universe came out from the Big Bang. And here is its statistical quantification. Okay, so if you just look at this picture, it looks like some random noise. You'd say nothing very interesting there. Okay, well, as physicists who use mathematics, what you have to do is analyze this picture on its own terms. So what's going on in this hot material coming out of the Big Bang is it's called a plasma, and this is the topic of the conference this week in Edinburgh, plasma physics. There's a million plasmas in this talk. Plasmas are everywhere. A plasma is just like a liquid made out of ions, electrons, and photons, particles of light. And this liquid supports sound waves. So just like the air in this room, sound waves can travel through it. And so you should think of this hot surface we're seeing as actually oscillating. These wiggles on the surface are really waves, density waves in the hot early universe. And what happened is that, to understand that, you need to look at this so that you see waves of a certain wavelength together, right? And you don't see that in this picture, but if you do what's called a Fourier transform of that picture, which means that you just look at this picture again, but in terms of wavelength, you see these beautiful curves. Okay, so the red curve was a theoretical curve predicted in the 1970s, and the blue points are the data, which are, as you see, in fantastic agreement. So again, this is showing us that the laws of physics we knew in the 1970s as just gravity and plasma physics fit what is seen beautifully. Now, I was very lucky that in the 90s, I was actually at Princeton when that very first curve was revealed, showing us the Planck spectrum. And then we got calculating, and we calculated the polarization of the radiation coming off the Big Bang. There was nothing original about this calculation. All the mathematical machinery had been developed by a physicist called Chandrasekhar in the 1930s. So we just used that, and we used the Einstein equations, and we calculated this red curve. Okay, now the amazing thing is that if you fit the parameters in the universe, so basically 5 numbers which you fit to the, which characterize the ingredients I mentioned on a previous slide, you fit those 5 numbers to the observations, then you predict this without any additional freedom. Okay, so this is either right or wrong. And as you can see, it fits perfectly. So what do you conclude from this? Not that we're very smart, it's that the laws of physics we learned here on Earth apply throughout the whole universe in the most incredibly precise way. It's very rare you fit anything in science without any adjustable parameters, and the large-scale universe is one of those things. So it's extremely simple. Now, that's the large-scale universe, okay? And I hope I've persuaded you that it's really simple to characterize. And mathematical description works extremely well. What about the universe on the tiniest scales? So you need the most powerful microscope. That's the Large Hadron Collider in Switzerland. It's the most powerful microscope ever built. It's a ring 27 kilometers around, and it just piles in protons and antiprotons at extremely high energy to try to see what they're made of. And so that's the most powerful probe. The one thing it discovered, which actually was predicted 50 years earlier by somebody in Edinburgh. Who was that? Peter Higgs, right. So I'm very fortunate to hold the Higgs chair, which was created when Peter Higgs won the Nobel Prize for this prediction. So it was found in the most expensive experiment of all time, the Large Hadron Collider, €10 billion experiment, 50 years after Peter Higgs predicted it. So again, how could that happen? Was he that clever? No, it's nothing to do with how clever he was. He was very clever. But it's that the laws of nature are really simple, okay? And once you get them right, they tell you what's going on. So here's Peter Higgs' paper, right? This is the paper he published on the Higgs boson. And it's only 1.5 pages, okay? Tell me that's not simple, okay? So a few little equations in here, and if you read this properly, it says equation 2b describes waves whose quanta have bare mass, blah, okay? That's the only prediction in the paper. And he only added that because the referee said, I don't like this because you haven't made any predictions. So he added one sentence, okay? And that eventually won him the Nobel Prize. So he should be grateful to the referee. So here is Peter Higgs. sadly passed away last year, but he lived in a top floor flat in the new town. He was an absolutely amazing person, probably the most humble and shyest person you could imagine. Many interesting stories about him. Very kind, very gentle person, but with very strong ideas. And here he is at the Large Hadron Collider, and I guarantee you he has absolutely no idea how it works. Okay, that's not what he does. Okay, he figures out what are the basic rules of the game that nature works by. Okay, so this is the standard model. This is the entirety of the basic ingredients of which everything in this room are made. And it's called a standard model. So they're quarks. These are the particles making up neutrons and protons in atomic nuclei. The electron is here, and some other versions of the electron, and strange particles called neutrinos. And I'm going to tell you they have something to do with the dark matter. And then you have the Higgs boson, which sort of couples to everything. And these are the forces. Electromagnetism is here, and the nuclear forces. And then we have gravity encompassing everything. Okay, so the story is the same as on the very large scales. Large scales was a surprisingly simple story. On small scales, same thing. So you built this 10 billion, we built this 10 billion euro machine. It found the Higgs boson, predicted 50 years earlier, and it found nothing else. Okay, so there's been no deviation from the standard model up to 10 TeV. That means, as a microscope, the size of a proton, if you imagine the size of a proton, a nuclear particle, go 10,000 times smaller to see if there's anything there. And the answer is no, there's nothing there. Okay, so that's what LHC has found. So what is this simplicity telling us? The surprising simplicity on large and small scales telling us something. And maybe it's that the laws of nature are actually very simple on very large and very small scales. And that's really optimistic for somebody like me, because it means maybe we're close to understanding the unified laws of physics. So here's all known physics. I won't try to describe it, but I want to get it across to you that we can put it all in a single equation. Okay, so this equation explains, matches every known natural phenomenon. Okay, it's sometimes very hard to work out its predictions, like how does my brain work? Okay, in principle, this describes it, but of course your brain is an awful lot more complicated than an atomic nucleus. So in practical terms, we can't use this equation for anything on a human scale. But this describes gravity, it describes forces, particles. Higgs gets 3 terms in this equation. He's a lucky guy. And you see there's some funny characters in this formula. There's I. I is the imaginary number. It's the number whose square is -1. Okay, this was used in 1500s to solve quadratic, cubic, quintic equations. It was realized that this was a very powerful tool to solving equations. And in 1700s, Euler, the mathematician Euler, came up with this incredible formula that E, which is a number comes out of calculus, it's like exponential growth, right? And I is this number which was useful in mathematics. I squared is -1. Pi, you know from geometry, the area of a unit circle is pi. And then 1 and 0, of course, the most basic numbers. So Euler found this amazing formula, and the same number I appears at the heart of physics. Okay, so again, this is telling us that somehow mathematical understanding is incredibly powerful when applied to nature. By the way, I can't help mentioning, but Euler, my recently graduated student, reading back in past papers, realized that Euler is the person who first wrote down F equals ma. You probably heard about F equals ma, and everybody says it's Newton's Newton's law of motion, okay, but actually Newton never wrote it down. It's Euler's formula. And Euler actually also made the first accurate map of Africa, as it happens. Very interesting person. So this formula underlies essentially every modern technology, right? Cell phones, electric light bulbs, everything depends on Maxwell's equations and essentially on all these equations. On that equation I wrote down. So nuclear fusion, which is sometimes called a star in a jar, kind of nice phrase because we live right next to a nuclear fusion reactor, the sun. And now people like Fulvio are very ambitiously trying to make a little sun in a laboratory in Nottinghamshire with a target of 2040. So Fulvio is not allowed to sleep at the moment. It's an extremely ambitious target and very, very exciting. If this fusion project works, we will untap an extraordinary amount of energy. And in principle, it can be clean energy. So these are some recent experiments inside a tokamak reactor. This is a planned reactor in Nottinghamshire. And as Fulvio said, the physics is extremely complex inside this. Holding the plasma, confining it with magnetic fields is a very, very challenging task. Okay, but what goes on in these plasmas are processes like this. So I'm going to tell you about our crazy idea about the universe. I've got 5 minutes to do it. Okay, so here's time and here's space. So here's an electron, one of the simplest elementary particles. Imagine this electron is traveling along in space and traveling through time. So it's following some line like this through space and time. And then imagine that that electron turns around and goes backwards in time. Okay, wouldn't that be cool? Right? We could just, if I could walk along and get faster and faster, and then I actually have to go faster than the speed of light, and I go so fast that I turn around and go backwards in time. It's not allowed according to the classical laws of physics, but it is allowed in the quantum laws of physics. And in fact, it happens all the time. So imagine the way you see this, if you slice this picture at a constant time, when you see the electron going backwards in time, you don't think it's an electron, it's actually a positron. It's an anti-electron. And what's going on in this picture is that an electron and a positron are meeting and annihilating into a photon. Right? That's this gamma. So this is E plus E minus annihilation. And the converse of this process is you can send in a photon, or actually an electric field, very strong electric field, and you can pair create an electron and a positron. And both of these things are seen all the time. Okay, so these are real processes. This one was predicted by Dirac, and then observed by the daughter of Marie Curie in 1933, which won her a Nobel Prize. And then this process, which is its relation, was predicted by John Wheeler, who I knew at Princeton when I was there. John Wheeler was an amazing person who dreamt of the name black hole. It's due to Wheeler. And he actually predicted this converse process in 1934. So a photon comes in and pair creates. By the way, there was very precise experiments done on this at the Relativistic Heavy Ion Collider in Brookhaven just in 2021. So what you do is send in 2 atomic nuclei. They're very strong electric fields. And when they get close, these 2 electric fields just pair create. So you see the electron-positron pairs coming out. Now, why have I related them like this? Okay, so just ask somebody, how is this process the same as that process? Well, it's obvious. You just do a rotation, right? Just turn it upside down. But in relativity, I'm not allowed to do that rotation. Mathematically, I'm only allowed to do what are called boosts. But when you introduce complex numbers, the number I, you do a complex boost, that's actually a rotation. Okay, so it really is a rotation in connecting space and time that connects this process to that process. It's called CPT, charge conjugation, parity, and time reversal. It's the most fundamental symmetry known in physics. It says that for any process involving particles, there's a similar process involving antiparticles, but it goes backwards in time, and actually you have to invert space through a mirror as well. So I'm not going to say any more about this, except that this is a very, very deep symmetry of the most elementary particles. And it's a consequence of relativity and what's called complex analyticity. It's a mathematical property. So this is our hypothesis, that the universe is symmetric under this process. Okay, why not? Either it is or it isn't. Okay, you've got a symmetry of the laws of nature. Either the universe respects that symmetry or it breaks that symmetry. The simplest possibility is it respects that symmetry. Okay, so that was our hypothesis. Now, how could it respect that symmetry? Here we have a universe coming out of the Big Bang, okay, dominated by radiation. It's making atomic nuclei by fusion, and then it makes galaxies, and so on. And it turns out that if you extrapolate the Einstein equations through the Big Bang singularity, you find this mirror image universe on the other side. There's just a mathematical operation, and it's full of antimatter. Okay, and it's literally so you can think about this process. You see, this has some kind of energy coming in and creating the two wings coming out. You can think of this as, if you like, as something comes in and creates these two wings coming out. It's really the same, except it's completely unnecessary for anything to come in. There's no need for any energy. The energy in Einstein's theory is always zero. So in this way of looking at it, the Big Bang is like a mirror, and you can think about this as the method of images. Again, a mathematical construction which allows you to impose certain conditions, boundary conditions. I told you I'd explain what the dark matter is. Here it is. Can you tell me the difference between the previous picture? I'll give you a clue. That was the standard model. This is the standard model with dark matter. What happened? That's the standard model, and that's with dark matter. Where's the dark matter? You see there's an L here. The standard model describes left-handed neutrinos. Everybody else has both left and right-handed particles. The neutrinos in the standard model are only left-handed. It turns out if you include the right-handed ones, just remove that L, now I have both left and right. Turns out in our picture of the Big Bang, one of the right-handed neutrinos behaves like dark matter. And in fact, there's an experimental prediction which should be checked in the next few years. Maybe that's the solution of the dark matter. So again, it's again trying to find the very simplest description. So I'm going to end on this slide. This is the future of the subject as I see it. We are here. We're looking back at the Big Bang. As I explained, that red circle shrink. As you go backward in time, the universe is shrinking. Okay, so the red circle would be here. And if I follow the universe backward in time, it's shrinking down to a point. And we get to this very, very far past where the observable universe, the universe we now can see, is only 10 microns across. Okay, and this is moved on the slide. I'm sorry. This distance should be from the bottom tip to the gray circle. That's 10 to the minus 43 seconds. That's the Planck time. I now believe that's what we're seeing on the sky. We're seeing an image of the universe as it was at the Planck time. And here you can see the sort of bumps and wiggles, and those are what we see on the sky. So that's the theory we're developing. And I think I'll stop there. I was going to explain how complexity emerged out of this. We're very simple on small scales, very simple on large scales, very complicated in the middle. but I think I'll save it if there's a question about it. So thanks for listening. By the way, I forgot another sort of cool thing to look at. The oldest rock on Earth. Do you know how old Earth is? So the universe is 13.8 billion years old. How old is Earth? Yeah, about 4.5 billion years. Okay, so the universe is, let's say, 13.8 billion years. Earth, 4.5 billion years. Earth emerged after, well, we don't quite know, but we think our galaxy formed, and in the process stars formed and planetary disks and so on. So Earth is only a third the age of the universe. So this little bottle holds the oldest known rock on Earth. Comes from the Northwest Territories of Canada. It's called Acasta gneiss. And you can have a look at it and take it out and fiddle with it if you like. It's not valuable, but don't steal it, please. And you'll see it's really, really hard and dense. And so this is how the very hot material in the core of the Earth came out and cooled and made this incredibly dense form of rock, which is 4-point-something billion years old. Okay, that's just a little bit of context about where we are now. Okay.
Right, thank you very much, Neil, for the beautiful lecture. It was really inspiring and fascinating. I've got a few questions for you that hopefully the audience will like. Let's start with your main claim. You basically argue that the universe is simple.
Yes.
But for most of us, the universe feels really not that simple. Try to assemble flat pack furniture, for example.
Right.
So can you tell us again, what do you mean by simple, and why should we find that remarkable?
Right. So simple, in my view, means understandable. And what does understandable mean? Understandable means that you really feel you know everything important about what's going on. Okay, so the universe is just happens. It's very surprising that it is remarkably understandable, regular, symmetrical. These are all words used to describe mathematically describable things. And yes, I would say that's just how things have turned out. So while most of my field, I believe, has confused itself by being insufficiently guided by observations and experiments. Okay, so human beings, we're all very, how should I say? I think especially in the modern age, we're very easily influenced. There are little schools of thought which develop, and trends and bubbles of thinking not related to reality at all, whereas the universe is actually teaching us how it is. Okay, and yet most people are, you say, so what's happened is people stuck to certain assumptions and frameworks very rigidly. And they convince themselves that the only way the laws of physics can be consistent is if there are extra dimensions of space, if there is a process called inflation, which is a sort of early blow-up of the universe, which turns out to be completely unnecessary in this picture. And in fact, if there's a multiverse. So people convince themselves through logical arguments that the universe we are in is not unique, that there are other universes out there. This is the least predictive scientific theory ever proposed. Okay, I don't think it even qualifies as a word theory. Okay, but nevertheless, it came extremely influential in the field I work in. So I think, on the contrary, we should learn from nature. And nature is always our best guide. I think, looking at these pictures, and many more I can show you, it's hard to argue with the fact that the universe is the most beautiful thing we know. It's stunningly beautiful and ordered and well organized. And I also find in the universe the fact that collective phenomena are extremely important. You know, in today's society, people think that individuals, you know, I was listening to something a week or two ago, and it was somebody trying to define intelligence. And so, and this is an AI type person, and so the way they defined intelligence is good at winning, okay? And they were meaning individuals good at winning. And I think that's the most absurd, ridiculous notion you can have. Because, and again, the universe tells us how to be good at making complexity. That's what the universe is good at doing. And how you're good at that is that you have collaborations, whether it's between atoms, between different forms of life, you have diversity, and you have collaboration. That's what's going on in the universe. And that's how the universe has been able to make extremely complex things like us. And I think in some ways, and this is not a theory, but it's maybe a mental picture, what it appears is that the laws of physics may be optimized, may be the optimal laws for creating a certain level of complexity. Okay, that's really the only thing I can think of at the moment that would explain the laws that we see. They're rather minimal in the sense of being capable of making an amazing amount of complexity from the smallest possible set of laws. I think that's a very interesting idea, though I don't know how to quantify it yet.
And Neil, I think we will come back on the theme of complexity also later in the questions. But
sure.
It seems to me that what you're saying is that observation are kind of forcing us also to
yes.
think that the universe is simple.
Yes.
From the way I see it, the history of physics is a little bit like the cupboard under the stairs. So when something doesn't fit, you create another shelf, another box, or another label. But our observation then telling us that nature is actually tidier than the theoreticians.
Exactly. Yeah, no, I think theoreticians are usually very confused. And the tradition of particle physics is that what happened in the 20th century is people built a new accelerator and found a new particle. And so they said, oh, well, there's going to be another one at the next accelerator. So they built a new accelerator and they found a new particle. That's how all of these particles were found. But then at a certain point, around, the time the LHC was built, that stopped happening. So the LHC went a factor of 10,000 up in energy, right? And nothing there, no new particles. So for me, that's extremely significant and exciting. Most people like me would say, oh my God, my model is ruled out, because everyone was making models of more and more particles, and then none were found. So most people were saying, oh, this is really disappointing. How could nature be so mean as not to supply another particle? But I think it's actually the opposite. I think what's going on is we're learning that, in fact, nature is extremely economical. And it's very evident in cosmology. We are literally seeing the entire observable universe, and we see no evidence of complexity at all. Everything we see on the large scales can be predicted with extreme accuracy and minimal assumptions.
And okay, so this also leads to probably a quite ambitious question, maybe a bit dangerous. The next leap in physics, is it going to be fundamentally produced by reducing ingredients in our equations or
yes.
adding them
right.
in a different form, if you want? Do you think that if you had to bet, let's say,
yes.
the next, are we closer to find new laws of physics, or are we closer to realize that the simplicity in the laws of physics will generate everything
yes.
that we actually see?
Yeah, the second one. So I think the big puzzle in basic theoretical physics is how to reconcile gravity with quantum mechanics. This is called quantum gravity, because they a priori look like they work very differently. And so this is the huge challenge, and it's related to this cosmological constant. The cosmological constant is the energy in empty space. And this is we have many kind of worries that in fundamental physics, empty space is full of vacuum fluctuations, and this actually gives you infinite energy, whereas the measured one is finite and small, but positive. So these sort of ideas are really the big challenges. And people have been trying to solve them by adding all these additional structures. It now appears to me that reconciling gravity with quantum mechanics is not necessarily going to be adding anything. It's just understanding the rules of both of them better. And I think the situation I like to compare with is, Einstein came along trying to understand gravity and how it was compatible with light and relativity and so on. And to understand gravity, he had essentially one clue, okay, which is Newton's law of gravity, but that didn't really help. The main clue was that if you drop two objects of different material composition and different weights, they fall at the same rate. Okay, that was the big clue, which Galileo had first observed. Okay, it's a 300-year-old clue. And that was the clue Einstein needed to get to realize that the reason they fall the same way is they both live in the same curved space-time, and they're both responding to the curvature, and their mass is irrelevant. Okay, so that was the equivalence principle. So he had one bit of evidence, and he figured out the law of gravity. We've got all this evidence. We've got these amazing clues. There's a cosmological constant. There are these beautiful scale-free fluctuations coming out of the Big Bang. We've got so many clues. I think if we can't figure out the next, step in the laws of physics, we should be shot. Okay? We've got clues coming out of our ears compared to what Einstein had. And I think the most important thing is to worry about the basic concepts in the field, and most important, encourage young people to worry about the basic concepts. I don't think the data is going to lead us to the answer. Some people, again, machine learning type people say, just gather lots of data and the answer will be obvious. I don't believe that at all. Okay, it's going to be somebody who's going to figure out how to reconcile the things we know.
Neil, let's go back for a second to complexity. You were mentioning it earlier. To a certain extent, one nice thing of the fundamental ideas is that they don't necessarily remain fundamental forever. They then lead to innovation and to technology that has practical application for all of us. And many of us physicists are actually working on this applied technology, and I know that very well as a fusion scientist. Yeah. Now, the question for me is, do you think that the fundamental ideas can help us understanding also how to solve problems that have a higher degree of complexity, and how? For example, for me, of course, it's fusion energy, but there are plenty of other applications.
Yes, I do. I mean, when you think about the fundamental laws of physics, they are very difficult to solve mathematically. Okay, so I wrote down this formula, but actually getting predictions out of that formula is incredibly difficult, usually. It requires supercomputers, it requires very powerful mathematical techniques. Those techniques don't change anything about the formula, but they're just simply trying to figure out what are its predictions. And so in the process of figuring that out, people develop very powerful methods. One of the things, for example, in that formula is an I. And the I could stand for interference, okay? So interference is a phenomenon with light that, you get diffraction patterns. If you just stare at anything, you don't see, it's always spread out by what are called diffraction and interference. Radio waves spread out and interfere with each other. This interference is described by that exponential of I formula. And making sense of that requires a combination of sort of very sophisticated mathematical ideas and heavy computation. And so I think that is going to be very fruitful in the future. Not just brute force computation. In fact, if you try and put that formula on a computer, brute force, it'll fall apart immediately. It's absolutely hopeless. You need a combination of analytical mathematical methods and powerful calculus. So, yeah, that's why I'm rather skeptical that, you know, AI is going to solve everything, because in the former, in the respect of using powerful analytical formulae, it's far behind human beings.
Yeah, very interesting.
Okay.
So we've been looking at a little bit like now applications that are good for the world as it is now, but let's now try to imagine what happens in 20, 40 years. What do you think is going to be the areas where our understanding is going to get much better? Is it quantum gravity? Is it dark matter?
Right.
Is it anything else?
It's impossible to predict the future. I hope we survive. I hope we will be wise enough to realize that if we can survive, these laws we've learnt about the universe, what they tell us is that there is an incredible future ahead of us. There are sources of energy, like fusion, thinking bigger, like black holes. You can use black holes as a source of energy. There's no real limit on how far we can travel through the universe. I mean, relativity is an amazing thing. So, for example, if you ask, could I travel to the other side of that picture, the whole span of the universe, in my lifetime? And the answer is you can, thanks to the laws of relativity. So, you know, at the moment we're sitting in this room, we're feeling 1g, one gravitational force, or acceleration of 1g. That's what it feels like. If we were on a rocket ship in space going with 1g, an acceleration of 1g, we'd feel very comfortable. Okay. If you traveled at 1g for 23 years, you would be on the other side of the universe. It's a very strange thing, because you go up to near the speed of light, and as you get faster and faster, the space contracts. That's called Lorentz contraction. So the universe is such as to allow us, the laws of physics allow us to explore it. The laws of physics allow incredible other things. You know, we can now measure time to 10 to the minus 19 seconds, clocks. And these clocks are very far from the limits. They can be far more accurate than that. So quantum technologies offer enormous increases in our capabilities. And there are many other examples, like detecting gravitational waves. These will be useful for probing the Earth, understand what's really going on in the interior. All of the stuff in the interior, is it usable? Probably it is. But you know, we need to scan it. So yeah, I think we have an extremely bright future, if only we can be wise enough not to destroy it.
and I think I actually want to end on this, in the sense that my last question is not going to be technical. It's going to be more on the human side, and I need to read it because there is you know, I'm citing something from your abstract. In your abstract, you basically say that knowledge of the universe is humankind's most precious possession and free to share. In a world that doesn't feel very cooperative at the moment,
Right.
I mean, what gives you confidence in this?
What gives me confidence is that I'm lucky enough to be involved in making these maths institutes, mathematical science institutes in Africa. And I've been fortunate to work with people there, and there are now 6 centers, and we're planning 3 more in the coming year, one of which is in DRC, which is the most ambitious program. But every time I go to Africa and I meet young Africans interested in science with a sort of freshness and enthusiasm because they've been starved of it, it fills me with hope. I think Europe and North America are sort of tired old continents where people have sort of lost the plot, and you see that in many ways. Africa hasn't really had a chance yet. And so that, when you see that sort of freshness and enthusiasm about the same things, we all love the same things, then that fills me with hope. But I just hope we can stop the people in California destroying the planet before the full range of sort of diverse human talent has a chance to work on fundamental science and technology, because we can just achieve so much more than we have already.
And this is probably a good note on which to end our conversation. So let's give a round of applause to Neil.
Thank you.
And now we have plenty of time for questions from the audience. Let's start with one question per person, please, and then we'll see if there is time for more. There are microphones, so people will come to you. If you have questions, just raise your hand, and I'll give you possibility of asking questions. Over there.
Thank you. That was a really inspiring talk.
Thank you.
I was interested in your views in the book that you published, I think it was about 12, 15 years ago, which to me had quite an optimistic note about the future and so on. A lot's changed since then.
It has.
And so really my question is, do you feel as optimistic now as you did then? Has anything, what do you think the differences are?
I'm still extremely optimistic. I mean, the source of my origin, my optimism is my parents. My parents were activists against apartheid in South Africa. And at that time, this was in the 1960s, 1970s. It looked hopeless. The society was very strong. South Africa had nuclear weapons. It was a very advanced and powerful state, and looked hopeless to change it. And both of my parents actually went to prison for opposing that. And life was very pessimistic. But they held on to the belief that ultimately this will change. And then in 1994, it changed. There was a free election. Mandela came to power. Both of my parents got elected to parliament. And suddenly they went from being pariahs to being, model citizens or, politicians. But my father became chair of the ethics committee in parliament. So I saw how quickly things can change. So that I've been very fortunate in. And I think we're going through a very rough patch now where people have made a lot of bad choices. But I do believe they're going to see that. I am very hopeful. I have to say I've just come back from the US, which I go to fearfully these days. But so I think they're in sort of rock bottom, but there are hopeful signs there too. I am still optimistic. I think the challenge is enormous, but we really have to try to encourage people to think for themselves, to learn lessons of history. We don't want to repeat the disasters of the past. I agree it's hard to be hopeful. But I think humanity has come through incredible problems in the past, and we will again.
History is for society, a little bit like data are for science, right? So
yes.
we need to learn from that.
Yes.
Question there?
Thank you. I find your talk very interesting. On that point, actually, as you say, we've got so much evidence now and so much information and data, but given the points you've just made, that is all stored electronically, and the first thing that anyone wants to do when they want to control a society is to destroy books, destroy that data. So
right.
Your point about sharing knowledge and getting us all to understand this,
right.
I think is really important, because the more people who have that collective knowledge,
right.
the less it can be erased from history, because
exactly.
it only takes somebody to wipe a database or to
exactly.
remove things from archives. So this is a really important thing for us all to be here to understand this and actually to
I agree.
Be engaged in
sometimes I say that physics is a subject for people with very bad memories, okay? Because, so when I was young, I loved biology, and I still think biology is the most interesting subject, because life is more interesting than physics. But you have to remember a lot of things in biology, right? It's a whole collection of historical accidents, and then, life is wonderful and incredibly diverse, but very hard to remember all those Latin names. In physics, you don't really have to remember anything. That's the whole point of it. That it's a logical machinery which, once you've understood it, everything follows. And the reason that's possible is because what we're describing is actually very simple at heart. So I think this form of knowledge, mathematical, the understanding of mathematical laws of nature, is indeed incredibly powerful and can be transmitted and maintained by people independent of any computer farm or whatever, right? Because it involves thought. And so indeed, I completely agree that sort of sharing that form of knowledge, even if all the computers in the world disappear tomorrow and all the databases disappear, we'll be able to recreate all of modern technology from that understanding.
I believe we have another question there.
Neil, thank you.
Yeah, yeah.
Did it work? Yeah?
Yeah.
I'm intrigued by the picture you showed of the Big Bang, and on the one side was real matter, on the other side the antimatter.
Yes.
So in your opinion, on the antimatter side, is there an antimatter EICC, and in it an antimatter version of us, and
yes.
Is the antimatter version of me left-handed like me, or is it right-handed like? If you could explain this, I'd be very appreciative.
Yes. So, okay. So, great. There it is. So we found this by extrapolating the laws we believe, Einstein's theory of gravity and the laws of plasmas and fluids, through the Big Bang. And it turns out there's a unique extrapolation mathematically. But is it real? Is the other side real? Okay. So the analogy I would make is with a mirror. So there are two ways to solve Maxwell's equations for light in the presence of a mirror. The first is the kind of most obvious way, that you take the mirror, the light comes off your face, it travels through space. It's made of electric and magnetic fields. There's a boundary condition at the mirror that the electric field tangential to the mirror must be zero. Okay, so you impose that boundary condition, and that causes the light to reflect and come back into your eye. So that's the way, you would do it, just using those equations. You have a boundary condition. Now there's a second way to do it, which is if I'm right-handed, I make a copy of myself that's left-handed, put that copy behind the mirror, throw the mirror away, and look at it. And that's what I see. And that's called the method of images, that you replace what is a boundary condition at the mirror by using symmetry as your guide. So this is the symmetry guide. This is the method of images. You can now ask, okay, could I get the same result just by chopping off the universe here and imposing a boundary condition there, just like at the mirror? And the answer is yes, you can get the same result. We just put out a paper last week on this. You'll find it online. I have a very bright Greek student who realized this. And there is a very particular boundary condition. As you know, space-time, you should think about it as a sort of flexible thing, like an elastic sheet or something. An elastic sheet can have a boundary. Now, what's the boundary condition? Well, either you fix the sheet, to some metal rod or something, that would be a fixed boundary condition, or you can have a free boundary. So I wiggle the sheet and it just flaps around because it's free. So this picture turns out to be equivalent to a free boundary condition at the Big Bang, okay, mathematically. And so the other side doesn't have to exist, but there is a very particular boundary condition which is the simplest. And by the way, Stephen Hawking, who I worked with, had a lot of my ideas are influenced by him very strongly. He had an idea called the no boundary proposal. And his idea is that you would follow space and time backward to the Big Bang, and then they would smoothly round off. So there was no clear beginning. There's just no boundary. It's like a bowl doesn't have a beginning. There's no boundary to a bowl except the top boundary. So he said that, this is the the current universe is one boundary, but there's no other boundary. His proposal should be called the no other boundary proposal. So that was his, and I worked for a long time on that, and it doesn't work. It just gives the wrong predictions. It predicts an empty universe. So we are now proposing that instead of the no boundary proposal, there is a free boundary proposal, which basically says that the Big Bang is where the universe flapped freely. And by the way, the same proposal holds for black holes. Black holes are very mysterious because when you fall inside a black hole, you hit a singularity. It's like the Big Bang in reverse. And our proposal is that at the last visible surface of a black hole, called a horizon, is actually a free boundary. And so it moves outward at the speed of light. So as you approach this horizon, in fact, you're not going to fall into the black hole. You're going to hit the boundary of space-time. So, yeah, we're playing with these ideas.
It's interesting that also in plasma physics we have this method of images in certain calculations.
Yes.
So physics is one and it's simple. It's
Absolutely.
the universe. Next question.
Hi, Neil. You mentioned how you don't think that machine learning is going to help some of the issues, answer some of the questions that we have, and as much as people think maybe. And you also mentioned supercomputers. So I was wondering, so it's two questions. What role do you think quantum computing will play in this? And also purely from a technological point of view, who do you think is leading in that space?
In quantum computing?
Yeah.
Well, it's very hard to compete with the big companies. They have accumulated such enormous resources that they can do, hundreds or thousands of times bigger efforts than any government. So it's hard to compete with them. I think, quite frankly, I think quantum computing is very interesting, but honestly, at the moment, only seems to apply to certain very specialized problems. It's very good at solving problems which aren't particularly interesting. Okay. The world itself, as far as we know, is a quantum computer. That's how the world works. That's how atoms work, and so on. But to try to, so to try to build a pure information processing machine out of qubits. I think the laws of physics are all about processing information, but nature seems to do it a lot better than we can do it. And if you build a computer out of qubits, there are varieties of methods used. So far, they're still pretty limited. So I must say, I generally feel that every penny spent on science is usually worthwhile. I mentioned that Large Hadron Collider cost 10 billion euros, a lot of money. But if you think what came out of it, it's extraordinary. There are like 6,000 young physicists there who are learning amazing sets of skills and who go into industry and companies and do all kinds of things. So I think money spent on basic science is never wasted. However, it's the way quantum computing is being sold as promoting growth, I think is utterly misleading. I don't think quantum computing is about to have any impact on the economy. Okay, sorry for saying that. So UK government has just given £1 billion to quantum computing with the justification this will promote growth. And I just don't buy it at all.
Neil, I will be cheeky and I will sneak in a question, which is a follow-up question from me. You've been working with Roger Penrose, and he claims that quantum computing might help understanding consciousness a bit better.
Right.
What do you think about that?
So Roger is just the most amazing theorist. He has his own ideas, and he is not driven by fashion at all. And usually what he's worked on has turned out 30 years later to be at the heart of some fashion, but he's well ahead of his time. So Roger believes that consciousness has something to do with quantum mechanics. I think basically the argument is that quantum mechanics is the the most powerful theoretical framework we have, and it does all kinds of really surprising things. And consciousness is the thing we understand least, and maybe these two things are connected. It's as simple as that. But yeah, I think his ideas have promoted other people to try to think, where is consciousness stored physically? We still have absolutely no idea, okay, where it is stored in our brains, or how it works, how consciousness works, how decision-making works in our mind. We really don't know. But I think Roger's ideas are probably the most provocative, and maybe, will have a glimmer of truth in them. He also believes that gravity may be connected to this whole process. And that's a very radical idea that, in quantum mechanics, there's a famous paradox, Schrödinger's cat, that is the cat alive or dead? It's only dead when you open the box and look. And before you open the box, it's both alive and dead. And Roger thinks that that's ridiculous, which it is, and that somehow gravity must be involved in quantum mechanics itself deciding before we look that the cat is either alive or dead. And so it has some collapse of the wave function. So he has some proposals for experiments to look for this effect. And I think that's a great topic to pursue. Very, very high risk, very unlikely his ideas are correct and complete, because they're very sketchy ideas. But I think he identifies really important problems, and yeah, if those are potentially, really important in guiding us to a better way of doing physics.
Okay, I think we have time for 2 or 3 questions. So I see one there.
Yeah, thank you.
I'll wait for the microphone. It's coming.
Thank you. You pointed out that LHC hasn't found any physics beyond standard model, but also we had to correct standard model because we have found that neutrinos have mass, and at least the original version of a standard model.
That's true.
And in one of your slides, you seem to imply that neutrino masses can play a role in explaining dark matter. So can you elaborate a bit on this?
I can, yes. So thanks for asking. I'm afraid I had to rush through that here. Okay, so there's a little bit of terminology here, which is annoying, that when people typically talk about the standard model, they mean this, where there are only left-handed neutrinos. But in this version of the standard model, neutrinos are not allowed to have a mass. Okay? We know this is wrong because neutrinos do have a mass, and the masses are measured in laboratory. Okay, so I don't think this should be called a standard model because we know it's wrong. How can it be the standard model if it's wrong? The simplest explanation, or the simplest addition to the standard model, which explains neutrino masses, is that, where you add right-handed neutrinos. And the origin of these masses is that as the left-handed guy is going along, the thumb is the direction it's moving, and the fingers are how it's spinning. So that we call that left-handed. We call this right-handed. So left-handed neutrinos look like this. And if you add right-handed neutrinos to this standard model, what happens is the left-handed guy travels along for a while, and then it mixes with the right-handed guy, actually through the Higgs. The Higgs allows them to mix. So it mixes, but the right-handed guy, if it's very heavy, then you realize you haven't got enough energy to be a right-handed neutrino, so you go back to being a left-handed neutrino. That's actually how left-handed neutrinos get a mass. They mix with virtual right-handed neutrinos. So that is the simplest explanation for the observed neutrino masses, that there are actually right-handed neutrinos. And the observations show, the observations only measure mass differences. Okay, so you've got 3 neutrinos, and the experiments measure the differences in mass between these three. There are 2 differences, and that's all that's measured currently. We don't know the absolute scale of the masses, so we need 3 numbers for the masses, but we only have 2 differences. That's current experiments. In our setup, what happens is that one of the right-handed neutrinos, there are 3 right-handed neutrinos, one of them is stable, and it's the dark matter. And if it's stable, that means it doesn't couple to the left-handed guys, because otherwise it would decay into them. So we have to actually decouple it from the left-handed guys. So 1 right-handed neutrino, which is stable, and 2 which explain these 2 mass differences that are observed. A consequence of this is that the lightest neutrinos should be exactly massless. That's our prediction. And that is now being tested. Amazingly, the most sensitive way of measuring neutrino masses is to look at galaxy surveys. It's very strange. But you see, the universe is a huge physics experiment, basically. Because it's so simple, the basic behavior of everything on large scales in the universe is so simple, you can use that to probe things like neutrino masses. So if the neutrino has a mass, has more mass, then a cloud of neutrinos gathered as part of the clustering of a big galaxy cluster, this cloud of neutrinos has mass. That means it clumps more efficiently under gravity. And so the clumping will be stronger in a universe where the neutrinos have mass. And that is now the most sensitive method we have of measuring neutrino masses. So we have predicted that the lightest one will be massless. This is going to be tested in the next 5 years. If it turns out to be massless, consistent with massless, this makes much more plausible that one of the right-handed neutrinos is the dark matter. Okay, and then there are other predictions which would follow, but they're harder to check experimentally.
Neil, we can try to have a final question. Probably this is the last one over there.
Thank you very much for your wonderful talk.
Thank you.
Actually, the idea of this anti-universe is very fascinating to me. Yeah. So the question is like, if we go to t equal to 0, right? Big Bang. And
yes.
the going for us, this universe, right?
Yes.
And your anti-universe is to the left, right?
Yes.
So let's say right we have this universe and left that's anti-universe.
Yes.
So my question is like, for that anti-universe, right? They may be going in their frame of reference, right? They may be going forward in time.
Exactly.
And for them, right?
Exactly.
So we are going backward in time.
Exactly.
So
So the short story is there's no difference between the 2 sides. We can't tell which side we're on. If we lived on the other side, we'd say, oh no, the other guys are the anti-universe. So yeah, there is no difference because this is a symmetry of the laws of physics. So if you turn the whole universe around, nothing changes.
Well, this was a public question. Final one, only if it's fast.
Thank you very much for your amazing talk. Just a technical curiosity. Going back to the observation of the cosmic microwave background radiation from Planck, for example, you see there are a lot of fluctuations in terms of density, polarization.
Yes.
Do you think it's really reasonable to assume that such fluctuation may arise from quantum fluctuation of the universe at the Planck era, maybe somehow amplified by inflation or?
Yes, inflation is not needed, okay? So indeed, exactly what we are working on is, it's this picture. Yeah, so this is quite a funny thing because if you read most of the literature, including most textbooks on cosmology, they will say you cannot predict anything before the Planck time. Okay, that's the folklore. This is completely wrong, okay? Just think about the LIGO experiment. So this is measuring gravitational waves. They have these 40-kilogram mirrors, which are very heavy, and they are measuring distances of about 1/1000th of the size of an atom, okay? How do they do that? Well, they don't do it atom by atom. They do it because it's a big object and it doesn't fluctuate much. So in fact, you're averaging over very, very many atoms. And that's how you suppress the noise, the quantum noise. It's the same with the Big Bang. When it came out, I mentioned this is 10 microns across. It's huge, okay? So even though on a Planck length, Planck length is 10 to the minus 35 meters, okay, tiny scale. On that scale, you can't decide what the geometry of space-time is because it's fluctuating. But we're 10 microns across. That's huge compared to the Planck. So you're a factor of 10 to the 30 bigger than the real scale. So it's a funny thing, but once you start to think about simple solutions, you realize that all of the previous assumptions people were making were actually not very well grounded. So I believe that this early universe, pre-Planck, is basically a macroscopic object. And the question is, what are dominating its quantum fluctuations? So we have developed an alternative explanation, doesn't need inflation. It does need some new ingredients, but those new ingredients are very much part of quantum gravity. So quantum gravity, I can explain in like 10 seconds. There is a simpler there is a simpler approach to quantum gravity. We're writing a whole bunch of papers on this right now. String theory convinced everyone that to describe quantum gravity, you need 10 dimensions of space-time, you need strings, you need supersymmetry, you need all this stuff. In the 1970s, there was already a very simple-minded guess as to how gravity works. Okay, so if you take the theories which do work at short distances, like QCD, these involve the field strength squared. The Einstein action for gravity involves the curvature, not squared. But you can add to it terms involving the curvature squared. It makes it look more like QCD. It was shown in the 1970s by a guy called Kelly Stell, who sadly passed away recently, that adding curvature squared makes gravity renormalizable. Okay, so there's a very simple-minded approach which has been sitting in the literature for a long time. There are problems and puzzles about it, but it's renormalizable, it's asymptotically free, and we now think we have a way of making sense of it, which requires understanding the basic laws of quantum field theory a little bit better, okay? But not introducing new particles, new forces, extra dimensions, all of that stuff. That, I believe, now appears as the lazy route, right? You don't question the orthodox rules. You just add stuff in the hope it will all simplify. And it doesn't simplify. It just gets more and more and more and more complicated. So yeah, that's my belief now.
But I guess that we will have to leave it at this.
Okay.
This was a great evening of science. Let's thank Neil once again.
Thank you.
Yes, thank you so much for Professor Neil Turok and Professor Fulvio Malatello for such an insightful and inspiring discussion. I think we'll all go away and just think on that. And of course, a huge thank you to yourselves. It's only through your engagement, your enthusiasm, your support that events like this can continue to